Thank you, and I thank the organizers for inviting me to give this talk, and also to the audience, and good afternoon to everyone. I will talk about information retrieval from black holes. So I will start with a brief outline of my talk. I will give a very brief introduction to quantum field theory in curved spacetime. Then I will go on to discuss the effect of non-vacuum states, the information paradox, and finally, can information be retrieved by quantum correlations? So these are the three papers on which this talk would be based on, and this work has been done in collaboration with Kinjal Klochan and Professor T. Padmanabhan at IU. So I start with quantum field theory in flat spacetime. So in quantum field theory, the basic thing that you deal with is the field itself. So these fields, excitations of these fields are essentially particles in the momentum space with a definite momenta, and they are relativistic. Now one sample problem, what you deal with in quantum field theory in flat spacetime is as follows. So you take an initial state, t going to minus infinity, you take an electron with some momentum k1, a photon with some momentum k2, and then you prepare a final state with an electron with a different momentum k3 and a photon with a different momentum k4. And you ask what is the scattering cross-section between them. This is one of the standard processes. Now before going into what I am going to talk about, there is one famous story. So a lion has escaped from its cage. And then the people of the zoo authority has gone to a physicist to ask what to do about it. So the physicist said it is very difficult to work with such a complicated shape as the lion. So let us start with a spherical lion. So I will start with a similar thing. So I'll make some simplifying assumptions, but that will encounter all the necessary details. So I'll assume that quantum fields are in some background geometry, a background field, which can be described using classical field equations. And I will work exclusively with massless scalar field so that the Lagrangian has only a kinetic term. Then the scalar field can be expanded in the field modes. So UK are the field modes, AK and AK dagger are the creation and annihilation operators, and it's integrated over the K modes. Now for flat Minkowski spacetime, the mode functions UK are just plane waves, but when you go to curved spacetime, that is no longer true. The Klein-Gordon equation do not necessarily have plane wave solutions. So what you do, you can have various kinds of wave mode functions, UK, VK under general coordinate transformation, and they mix up. For example, you can write a different mode function VK in terms of the mode functions UK and UK star. So there are different frequencies, positive frequency and negative frequency, they all mix to each other, and the corresponding coefficients are known as the Bogoliubov coefficients, this alpha and this beta. Now a nice question to ask that suppose I expand the scalar field, so like here I did in terms of the mode functions UK, if I do it in terms of VK, I will have some different creation and annihilation operator. So if I ask what happens to the number of B particles in the A vacuum, so you construct a number operator for the B dagger B creation and annihilation operator and construct the expectation value in the A vacuum. And it turns out that this is non-zero and given by the mod beta square where beta is sitting here. Therefore, the vacuum for A contains particles, B particles. Now what about excited states? So for excited states, I will only demonstrate it for a single particle excitation. So you have a function f omega. So this is a single particle state. If you apply the number operator value, this will give you the value 1. And then you can actually show that this gives a correction to the previous result. So earlier I had a mod beta k square, but due to this additional 1 particle state, you will have a correction, which also depends on alpha, beta, the Bogoliubov coefficients, and this function f. So if you know f, alpha and beta, you know the particular correction. This will be quite useful when I will talk about the information paradox. Now let us come to the case of black holes. So for black holes, you take a massive star that collapses, and at the end, neither the degeneracy pressure of electron or that of proton-neutron plasma is able to balance it, and hence you have a black hole. So it loses all possible information. The only 3 remains, mass, charge and angular momentum, and hence no hair. This is a one-way membrane, you can throw things in, but there is nothing that comes out, so null surface, and this is the Schwarzschild, famous Schwarzschild space. And this is the corresponding Penrose diagram, this is the singularity, this dotted line represents, this is the event horizon, and this is the shell which is collapsing and forming the black hole. And this is the asymptotic future infinity, this is the asymptotic past infinity on the null line. So now what is the paradox? Suppose I throw a cup of coffee into the black hole. Now in principle what you can do, you can go inside the black hole and see what you have thrown inside. But the main problem is the black hole evaporates thermally. And after a long amount of time, all the information about that cup of coffee is lost. And what you have is only an information about temperature and hence the information about the mass. However, sometimes it is argued that a Planck mass remnant might still be there, since semi-classical approximation would break down at some stage, But the Planck size remnant cannot hold all the information that has been gone into a black hole, and hence the real paradox. This is just a cartoon depicting the same. So you have a completely thermal radiation. The two guys are measuring it. There is nothing there. Then you ask that, yes, there is a remnant. Can it do the game? No, it's just a quantum gravity, but it cannot change the game at all. So I thank Kinjal for preparing this for me. Now, I will be interested in the retrieval of information. That is, from the spectrum at late times, can I tell what has fallen into the black hole? Now, for the Schwarzschild space-time, you define the vacuum before the collapse and after the collapse, and there is a change of geometry. Therefore, the Bogoliubov coefficients are non-zero, and they took the following form. Here, kappa is the surface gravity, these omegas are the frequencies, c is just a constant, and all the functions here are well known. Now, what you do? You first assume that you throw one particle into the black hole. So therefore, you take the in state as a one particle wave function. This f omega characterize all the things that you have thrown into a black hole. If you can recover f omega, then you have recovered the information what you have thrown into a black hole. So the job is, given this one particle state and the late time thermal radiation or correction to the thermal radiation, can you get f omega out of it? So what we will look at is this object in omega 1, omega 2. This is the cross correlation between two frequencies. The frequencies are omega 1 and omega 2, and you take expectation value with respect to this state psi in. So it can be written in two functions. One is A, the another is B. So these are the forms of A and B, and this N is essentially this cross correlation where you take B dagger and B at two different frequencies and its conjugate. And this function f, which is appearing here, is essentially the Fourier transform of the function f omega, which is given here. So this is your f, which is appearing in this particular expression, and this f is the Fourier transform. So if you know this function f, you essentially know about this function f of omega. So given this number expectation value, which is this n omega 1, omega 2 expectation value, you can actually take a derivative of it with respect to time and construct this following object, which is n omega 1, omega 2, you divide it, multiply by I and take a derivative. So when you do the same, what you end up getting, this is this particular combination. Now here, this D is what I have constructed here. So given n omega 1, omega 2, that is you measure after the black hole has evaporated, what is the number expectation value or the frequency correlation. So given that, you essentially know D, and all these are functions, omega 1 and omega 2. So all of this part is completely well known. Therefore, this side, which depends on f omega by k and f star omega by k, is also well known. Now, from this you cannot recover the full information. But suppose for an instant that you have a real initial state, that is f omega is f star of omega. Then by properties of Fourier transform, you know that f omega by k is f star of minus omega by k. And that helps to give you to this particular form. So what you can do now, suppose you fix omega 1 and you change omega 2, then you can actually extract this particular function. And similarly, you can do it the other way around. Now, since you know f of omega, and by this particular logic, you can put that relation here and get the solution for f omega. So therefore, just by looking at the spectrum at infinity or after a very late time, after the black hole has evaporated, you can actually tell what you have thrown into a black hole. But just we have demonstrated it for a single particle case. So therefore, the knowledge about the correction n omega 1, omega 2 will enable us to compute f omega by k, which is the Fourier transform of the function f omega. Now, the complete information about f omega by k requires some symmetries. So here we have just used a 2-point function, that is, I have just used psi and n omega 1, omega 2. So that essentially does not give us the full information about f omega. So unless I assume some particular real state here, I don't get the full information. Otherwise, there would be some ambiguities left, and that has to be dealt by either going to higher correlation function or by some other means. Secondly, the complete information requires some more symmetries like the real initial state. Now, having obtained this f omega by k, we can apply the inverse Fourier transform in order to get f omega, and thus even it shows that given a single particle state, and it will work for multi-particle states as well. Like if you have two such things, so here what we have done, so here I have given one a omega dagger, you could have given another a omega dagger. So that will be f omega 1, omega 2, a omega 1 dagger, a omega 2 dagger. So that would be a two-particle state. So that if you apply the number operator, you will get a result which is 2. So even for those particular states, you can apply the same procedure and get the corresponding f here. Now, what are the future outlooks? As I have already mentioned that we have only used 2-point correlation functions. The more information may be retrieved by using higher point correlation functions. And in these cases, we might not have to assume any symmetry. For example, here we have assumed the existence of a real initial state in order to retrieve the full information. But we might not have to assume any particular symmetry in order to retrieve all the information. The other point I would like to mention that we have just answered the question that how you can retrieve the information. But there is another paradox here. That is, initially you had a pure state, and that has been going to a mixed state, because the black hole starts with some particular configuration, and since matter is intrinsically quantum, it should be a pure state. But ultimately, after the evaporation, what you have is a thermal spectrum, and thermal states are mixed states. So how does a pure to mixed transition occurs? That is there any violation of unitarity? So that is another point we would like to explore later, but in this particular work, we have not explored on the aspects of unitarity, but only on the aspects of information retrieval. So I will now summarize a brief idea about quantum fields in curved spacetime, in particular Schwarzschild solution and non-uniqueness of vacuum I have presented by the Bogoliubov transformation. You can have UK, VK and lots of mode functions to deal with. Now if you treat matter fields as intrinsically quantum, like what you have thrown in is essentially a quantum field, and therefore it's an excitation over the vacuum. So I have chosen that excitation to be a single particle state, and if you do that in Schwarzschild spacetime, you can derive information about the initial state. Now the frequency correlator that I use omega 1, omega 2, that also has diagonal parts. On the other hand, I have used the off-diagonal parts, when omega 1 is not equal to omega 2. So these off-diagonal elements require the state to be real only, what I stated, but if you rely on the diagonal part, then it has to be real and symmetry. So something we have achieved by using this omega 1, omega 2 frequency cross correlation. And finally, the calculation has been done for 2-point functions, while the higher point functions might lead to more information. So with this, I thank all of you.
So if I understand correctly, you have started from the vacuum initial state, you have modified the vacuum by creating a particle. This particle will fall into the black hole, and then you have computed the expectation value in this state of some operators. But what you have not shown is that these operators can be measured outside of the black hole. You have not shown that these operators will be available and that you will be able to make the measurement and retrieve all this information while staying outside of the black hole, right?
No, but okay, let me get back here.
I mean, there is no location information about how I measure that quantity.
No,
you have not given me a procedure by which I measure that quantity staying outside of the black hole.
No, so the quantum field is defined over the full Cauchy surface.
Right, but to make sure that that I can do this measurement, right? I cannot do a measure, even though the quantum state of a particle on the other side of the universe is an excitation of the quantum field that is present everywhere. I cannot determine the state of that particle by making measurements here. That I cannot do. Okay, so you have not shown that I can measure those quantities by staying outside of the black hole.
Okay, but yeah, I mean, the argument that I essentially used was that this is a number expectation value. And
what is the process to measure?
Okay. I mean, I have two particular states, and that state is defined throughout. So just like when we did the thermal value for the Hawking, and then essentially
I can do the same calculation regarding a particle on the other side of the universe, but you cannot convince me that by making measurements here with apparatuses here, I can determine the state of that particle on the other side of the universe, even though I can write these equations.
Okay. Yeah, I mean, the way I would argue is the following. So you have Hawking radiation, and there essentially what you compute, you can take n omega 1, omega 2, and you take the vacuum state. So essentially you compute this n omega 1, omega 2 is defined for this Scri plus, and there you are computing this state for the other state's vacuum. That is, you have an in vacuum, and you are computing the expectation value of the number operator in the in vacuum. That gives you the thermal value. I'm just using the same prescription with a different state essentially. So
maybe we can take it offline, or you. So the point is, if you're saying we can do, so suppose there is another particle in the other part of the universe, the wave function would have some information of that, but you're saying, so effectively it will reflect in the correlation throughout the hypersurface. It will reflect into the correlation throughout the hypersurface. The hypersurface where on which excitation has been done, which change its behavior from the point of view of quantum correlations. So here also there, quantum correlations, yes. Yes, so phi x, phi y, if you can calculate over there, that will have some information if the state was vacuum or not vacuum. I'm saying the correlation will be different from vacuum. Phi x, phi y, that will be different from vacuum. That's what I'm saying. Okay, we can take it offline. We can argue about that. So correlation functions are non-zero on a space-like separation. That's why his statement is.
Other side of the universe. But if I restrict myself to measurements here, there is absolutely no way I can determine if somebody else have created a particle on the other side of the universe. That way you could have, faster than light communication if you could measure that.
It's not communication. It's not communication. I'm saying you will have the different correlation. For communication, you want commutator to be non-zero. That will still be zero.
Okay. If there are no further questions, then thanks, Afika, once again.